Greetings and welcome to another lecture in statistics. Now, this particular lecture is dealing with both correlation and regression because essentially they're both two steps in the same process. Once you find correlation, it's very easy to find regression, and we'll talk about why you might want to do that in just a little bit. But first, scatterplots. Now, scatterplots are when you have data and you basically plot it on a graph where you have one variable along the x-axis, the horizontal axis, one variable along the vertical axis, the y-axis, and therefore you could say, well, for when x is this and y is this, if x is 3, then we'll go count over 3 on x, and if y is 4, we'll count up 4 and put a dot there. Okay? So, and then when x is 6, y is 2, so we count over 6 and up 2 and so forth and so on. So scatterplots are one way basically of looking at data that allows us to view and compare the values of two variables. When x is this, y is this. And so therefore we can plot it on a graph. And there you could see a couple of different examples of different scatterplots. And when you do have a linear association, which we have in two of these, basically a linear association is when it's a straight line. Okay? Doesn't really matter what the slope is, whether it's going up or going down or horizontal, but it's when you have a straight line. And as you can see, in this one as well as this one, we have a straight line. We do not have any line at all here, and while here we have a line, it's not straight. This is actually called a nonlinear association, or it's also called a curvilinear, because as you can see, there's a curve. Now, curvilinears are not unusual when we're talking about data. It's not really something that we're going to necessarily be addressing here, simply because it's a little more complicated. But one example of curvilinear data that I can think of is if we have motivation here along the x-axis, and if we have a score on a test here along the y-axis. Because, yes, motivation is good to have. The more motivated you are, the better you're going to do to a point. However, it's possible to be too motivated. It's possible for motivation to be out here. And when you're too motivated, it's quite possible that you're going to have problems concentrating on the test. It's why we call it test anxiety. And so when you get really, 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 really motivated, then it's quite possible that your scores are going to go down. So when we're talking linear associations, we're talking, first of all, the direction. There's a positive direction and there's a negative direction. Okay? Do not be thinking about these in terms of value judgments. Okay? It's not that positive is good and negative is bad, or positive is going up and negative is going down. It's not like that. Basically, when there is a positive relationship or it's a positive direction, it means that both of the variables move in the same direction. As you can see here, as x gets larger, y gets larger. As x gets smaller, y gets smaller, and vice versa. That is positive. Okay? They both move in the same direction. That's a positive association. Now, a negative association is the opposite. When x gets bigger, y gets smaller. When x gets smaller, y gets bigger. It's inverse. Okay? It's still a line. It's just a line going this way instead of a line going that way. So, I mean, they're both linear relationships. The positive and negative simply tell you, how these two vary together. The strength is how well we can predict one variable when given the other. When it comes to scatter plots, the strength is how close, how scrunched together, shall we say, are all of the points on that line. Now, when we're looking at this one here, for instance, we're looking at this one, my goodness, that's a really nice line. Everybody can see that's a line. That's a strong relationship there. That is a strong correlation because it basically makes up the line. Now, this is still a line. There is still a line here. It's not as obvious, but you can tell that, there's a difference between here and here. So it's negative, so it's going in this direction, and it's a moderate strength. Okay, you can see it, but it's not spectacular. Down here, you have a zero strength. There is no line, or if there is, it goes this way. I mean, that tells us nothing. Neither does a line that goes this way. I mean, that basically, there's no relationship there. There's no relationship between x and y, because when you go into x, you can't predict, y is all over the place. If we go to x here, we got y, or even better, x is here, y can be anywhere along there. Okay, if y is here, x can be anywhere along there. There's no relationship. From scatterplots, we go to correlations. Now, correlation gives us the same information, but it gives it to us in a numerical form rather than in a picture. So correlation analysis is also known as Pearson's R. It was developed by a guy named Pearson, and he decided to use R for the abbreviation. And what this does is it tells us about the direction and the strength of association between two variables. Now, generally, when we're using correlations, what we're talking about here is not a cause and effect. We don't get cause and effect from correlations. Okay? They simply tell us there's a relationship, what direction the relationship is and how strong the relationship is. But it does not tell us the nature of the relationship. We have to basically, do more research to find out what that is. Do an experiment, perhaps, to rule out everything except a possible cause. So that gives us information, but remember, it doesn't give us cause and effect. Now, the range of the correlation is basically from 0 to plus or minus 1. And I write it that way very deliberately. Sometimes I've seen it written -1 to 0 to +1. And that's actually confusing, because here the plus and the minus have nothing to do with the size of the correlation. As you can see here, a correlation of -1 is equal to a correlation of +1. And that's one of the hardest things that people have to remember when they're listening or learning about correlations, is that the plus and the minus have nothing to do with the size. It has to do with the direction. If there's a plus, then it's a positive correlation. When one gets larger, the other gets larger. When one gets smaller, the other gets smaller. If it's a minus, then it's a negative correlation. When one gets larger, the other gets smaller. Nothing to do with the size. So if I happen to ask you on the test, for instance, what is the largest correlation or the strongest correlation, or what is the smallest or the weakest correlation, the best thing for you to do is to cross out the plus or the minus. Because the plus and the minus have nothing to do with the size. They have to do with the direction. And all they're there is to confuse you. A correlation of -0.9 is larger than a correlation of +0.5. How do you make sure? You take out the plus and the minus, and 0.9 is larger than 0.5. Do keep that in mind. Okay? Now, very often it's assumed or it's phrased as independent variable x affects dependent variable y. The problem here is that very often, as I've said, when we're doing this research, we're not doing experiments, so we don't technically have a true independent variable and dependent variable. Because, technically, the independent variable is the cause and the dependent variable is the effect. And we don't have a cause and effect because we have a correlation. So, but still, people tend to think of this as, x affecting y sort of thing. So it's phrased here as well. Just keep in mind that when we're talking correlations, it's usually from observations, it's from surveys, it's from case studies. It's not from an experiment. It's not going to give us cause and effect. Now, there's basically two different ways to find a correlation. There's the conceptual way, and there's the numerical way, okay, the mathematical way. Your book suggests we do the conceptual way, and I agree with it, because in a lot of ways the conceptual way is easier. It basically takes a number of steps that you've already mastered, that you already know how to do, okay? So it takes these steps that you already know how to do, that you've already mastered, and then we manipulate them in order to find the R statistic. Specifically, we find the Z-scores, and then we manipulate them to give us the R statistic. You know how to find Z-scores. My goodness, you've been finding Z-scores for weeks. Okay? That was way back before spring break. Back before the world changed. So you know how to do that. So, how to do it? Find the Z-scores. Okay? Now, I'm not going to go through this step by step. You know how to do it. I am going to give you a reminder, though. Because to find the Z-scores, you take the score, you subtract it from you subtract the mean from it, and you divide it by the standard deviation of that pool of scores. You are going to need to find the standard deviation for both the X scores and the Y scores. Okay? You're going to have to separate them from their association with the X scores or with the Y scores. You'll have to find the standard deviation for the X scores by themselves and the standard deviation for the Y scores by themselves. Don't worry, that'll be on the formula sheet. Okay? And that's why I'm putting this twice. Because, I mean, generally we use X to mean a score, but here we have X being a specific score. So I wanted to make sure you understand you have to do it both X and for Y. So for each case, for each point on that scatter plot, you have an X score and a Y score. Find the Z score for each. Find how many standard deviations it is away from the mean. That's what a Z score is. Multiply the two Z scores together. Multiply the Z score for the X and the Z score for the Y. For each case, for each point on the scatter plot. Once you have multiplied those two for every single case that you have, every single point on that scatter plot, you sum them up, and then you divide the sum by n minus 1. Kind of a degree of freedom-ish. Here's the actual formula. These formulas should be getting less and less frightening, because when you look at it, you can tell what it is. You take the Z score and the X score for each case. Okay, you sum it up, because you can't just do one big X score or Y score, because every case is going to have a different X score and Y score, so they're going to have different standard deviation for each. They're going to have a different Z score for each, and so therefore, then you divide it by n minus 1, and that gives us R. That gives us Pearson's R. Now, if you want to do it with the mathematical formula, the computational formula, you can. I don't recommend it. First of all, because here it is. Now, I mean, the good point about this is that you don't have to find a Z score. You don't have to do all those prior steps. The bad point about it is, first of all, you have to do that. I mean, it's not as complicated as it looks once you sit and start plugging stuff in. But yeah, I mean, that's kind of complicated. Okay? And it's not stuff we've done before. The other reason you don't want to do it this way is that if we're going to be finding a regression, and I can pretty much guarantee that we're going to be finding a regression for these, because after all, the regression is the second part of the chapter. That's what we're going to cover next. So you can pretty much expect to find a regression for each of these particular correlations that I have you do. The regression formula needs some of the stuff that you would find out for the computational. Specifically, the regression formula needs the standard deviation for X and Y. And if you've already found the standard deviation by using that conceptual formula, then you don't have to do any more math. You just have to, well, at least not to find the standard deviations. You have to plug everything into the formula, of course. But still, you already have a lot of it done. You already be part of the way there. So I highly recommend that you do the computational formula, and whichever one you decide to do, show all your work. Do it very clearly. Because if you make a mistake in the math and I can't find where the mistake is, you're not going to get partial credit. So if you've got numbers all over creation and I can't tell what you're doing or figure out what you're doing, then there's no way I can give you partial credit for it. So please make sure that you write everything down, everything clearly. Yes, you're probably going to use a lot of paper and take a lot of pictures of them to send to me, but hey, recycle the paper afterwards, and the partial credit is worth it.